Hello, everyone.
Hello.
So Noah, just quickly before we begin. Okay, so let me share my screen and hopefully everyone can see it. Is that
Yes.
correct? Okay. So today we're going to finish up concurrency, and then we're going to head into functional languages for the last 2 weeks of the course. I did want to say one thing about, there was a good question on Piazza about, this has happened in previous semesters too. If you decide that you're going to use my talk server to test your client, which is a fine thing to do, you need to know this about my talkserver.jar file. When it sends chat room information to the client, if it just sent it like this, which is the way my server sends the information, is it sends the name of a room, then it sends person name, room name, person name. So when I did it, I was assuming perhaps a person name could be multiple words, and hence putting all the person names on one line might cause a problem. So it's certainly, I think, legitimate to send it as room name and then just say all the person names are on the same line. But it is limiting in case the person did choose to put white space in their name. Now you can't know where one person's name ends and the next one begins. That's why I chose, when I transmitted persons' names, to put one per line, because that was unambiguous then about whose name, where one name ended and the next name began. But this created another problem, which is now, how do you distinguish a room name from a person name? There's really no good way. So I added a delimiter. I think I called it end participant. And that way, I knew when the person list for a room ended and I was getting another room. So if you decide to use my talkserver.jar to test your client, you need to be aware that this is how I'm sending the chat information. It comes as a room name on a separate line, and then the people in the room on separate lines. And then when you've reached the end of the person list, I send this end participant delimiter. And then at the end of when all the rooms are exhausted, I send an end room delimiter. And I'm not sure that you can get away with not having some delimiter at the end of your chat room data. The reason is that when you've reached the end of this chat room information, this is at the beginning where the person is being asked to choose a chat room. So when you get here, you want to display all that information to the user and then wait for a response. But you can't, you're not getting this isn't the end of the input on this socket, because later you'll be getting lines from other people in the chat room that you want to echo. So after this will come things like Plank, how are you, Goofus? Okay, so that's when you reach the end of this chat room information, that's not the end of data that's going to come on this socket. You're next going to be getting chat messages from whichever chat room you enter. So you can't just sit here thinking somehow the first chat message you get, you're going to magically be able to figure out that it is a chat message. And the second problem is you're not going to get chat messages until the person has chosen a room. So you really need to know when the room information has been completed so that you can print it out and get the user to give you a choice. So while you might be able to avoid using this end participant delimiter, I really don't see how you can avoid using a delimiter at the end of your chat room data. Just 1 second. So, but that's what, if you're using my talk server.jar file to test your client, because you develop the client first and you want to make sure it works, you need to deal with these two delimiters. And of course, then no person can be named end participant or end room, because that would mess everything up. Yes.
So should we also enforce that? I noticed that you did, but it wasn't anywhere in the write-up, so I wasn't sure if that's something you wanted us to throw in there or not.
I don't, so as I said, since I didn't say that a person's name couldn't be enclosed, that it had to have white space, I think it's okay that you just put the person's names on the same line as the room. But as I said, also, I don't think you can avoid the second delimiter with end room.
Right.
So,
That's my question.
but yeah, I think I'm fine if you decided to put all the people on one line. I did not intend to test with people who had a blank space. But I will say, in general, you should assume that people might have white space in their names when you're designing a real application. Other questions?
So our talk client does not need to work with your talk server?
Correct. Yeah, it does not need to. But
okay, I don't have end rooms.
Some people, pardon?
I don't have end rooms or end participants.
Yes,
I simply
fine.
traverse a map.
Yeah, that's fine. That's fine. No worries.
Okay.
But
cool.
it did occur to me after I got the question that whoever is testing in this way needs to know this format that's coming from my server, just so that they can make it work. But yes, again, to reiterate the person's question, you do not have to make your talk client work with my talk server. It's perfectly fine that you just design your own server and your own client, and the two work interchangeably. Other questions about the homework assignment? Okay. In that case, what we are doing today is finishing up our discussion of high-level Java concurrency mechanisms. And you'll remember, or you may not, so we'll just quickly go through it. There are basically 5 new things that were introduced. I think it was in JDK 7. There were mutex locks to not replace synchronized methods and synchronized statements, because if you're not that familiar with concurrency, synchronized methods and synchronized statements actually work pretty well. But if you really need to get into fine-grained control and deadlock is an issue, then they gave you the option of using mutex locks. The second thing is they introduced this notion of thread pools and executors for thread pools, which we will be discussing today. Then they introduced atomic variables like increment and decrement counters, some arrays of variables that you could do certain primitive operations on them without worrying about synchronization. So some very common types of variables that you might want to synchronize, they created predefined classes for them. Then concurrent collections, same idea that there are certain atomic operations you want to perform on a collection. For basically insert and delete need to be atomic, but they perform multiple instructions. So they introduced vectors, a couple other concurrent maps, a concurrent first in, first out queue that specifically were meant to be used in a multi-threaded environment. And finally, random number generators that could also be used without worrying about sharing a random number generator, or somehow multiple seeding a random number generator with different seeds and then getting unexpected random numbers. One thing I find is that beginners to Java often use the concurrent collections because they work even in single-threaded applications, but you should use the right tool for the task. And using a vector in a single-threaded application is like using a sledgehammer when a hammer would work. So vectors and any collection object that can be used in a multi-threaded environment incurs overhead in addition to the normal operation on the object. So if you use a vector, then the person has to acquire a lock before they use it. The lock is removed after they use it. The information is immediately flushed to memory. All of these things incur overhead that is not associated with an array list. So even though these concurrent objects work in single-threaded applications, you shouldn't use them in single-threaded applications because they slow the application down because of their locking and unlocking and their flushing of variables out to memory rather than holding them temporarily in registers. Okay, so last time we went over mutex locks, and basically they are designed to look like the locks on objects, but with the ability to back out if you cannot acquire the lock or to wait a certain amount of time. So lock is like a normal synchronized method. It just tries to acquire the lock and will sleep as long as necessary to get it. So that's like your traditional synchronized method or synchronized statement. Try lock will try to acquire the lock, and if the lock cannot be obtained, will fail and immediately return false. Or you can say, I'm willing to wait for some number of milliseconds, and if I can get the lock in that number of milliseconds, great, and if not, it fails and you can back out. And then lock interruptibility is like lock, which says I will sleep as long as necessary in order to get the lock, but unlike lock, I'm willing to be interrupted while I'm waiting. So if someone calls the interrupted method, I'm willing to be interrupted with an interrupted exception, and I will handle it. So last time, and then there is a new condition method associated with a lock that returns a condition object that is essentially allows you to use the wait and notify methods that are associated with synchronized methods. So wait releases a lock until some condition is fulfilled. Notify indicates that a condition is fulfilled and wakes up people waiting on that lock. So a condition object fulfills the same functionality. So it has an await method that basically releases the lock temporarily while you wait for some condition to be fulfilled. Basically, you're awaiting a signal for this lock. And then the signal method is like the notify method. It notifies other threads that the condition is fulfilled for this lock. And then, so you typically signal and then you unlock the lock so that other people know that the condition is fulfilled. So we went through the bounded buffer example Thursday. I'm not going to repeat that one. Instead, I have another example that I'm going to show you. So let's see if and then the class so lock is an interface, and the class we normally use the concrete class that we normally use to implement the lock interface is the re-entrant lock. And you'll notice one parameter that you can pass is who gets the lock next when it's unlocked. So by default, the parameter fair is false, meaning any thread can get it. But if you set fair to true, that means the longest waiting thread will get the lock to avoid starvation. So this is a way you can also avoid starvation. Okay, so I created a second example that involved adding together two numbers. And it's much like the competition that I showed you between Alphonse and Gaston, except that you're adding the two, think of it as adding the two scores together rather than determining which of the two scores is greater. Okay, so here is the example using synchronized method. So everything is synchronized, and you are creating a box for Alphonse and a box for Gaston and starting them up. And you can see that sorry, thank you. Hold on one second. Apparently my screen is not showing the right. There we go. Does everyone see code now?
Yes.
Okay.
Yeah.
I know here in the classroom there wasn't. It was still showing the PowerPoint slide. Okay.
We were on that same thing. Everyone was stuck.
Stuck. Okay. So let's then go back. So this is the bad lock thing. So we have a box object up here. And you create the box with a name and a value. And the big thing that it does is it adds two values together. So you give it someone else's box, and basically you get the value of that box, and you add this value and that value together to get a sum. So, and then everything is synchronized, okay? And then we have a loop that's going to implement runnable. And what it does is it takes two boxes, box 1 and box 2, and it creates a random object, and then it sleeps for somewhere between 0 and, 10 seconds. Then, or maybe 10 milliseconds, I think it's 10 milliseconds. Then it tries to add the contents of box 2 to box 1. And then it tries to reset box 1's value to a new random number. Okay, and it's in an infinite loop here. So basically what we're doing is we sleep for some number of milliseconds. Then when we wake up, we add the contents of box 2 to our value, which, as you saw, causes us to print out the sum of the two. And then we reset our value to a new random number and repeat. Okay, and we do this indefinitely. So this is bad luck. So let's go to run it, and it immediately deadlocks. So Gaston's value is 20, Alphonse's value is 10, and the problem is that, so essentially the problem is Alphonse started first. So we have Alphonse. So Alphonse started first, and in its runnable, it immediately went to sleep. So when it went to sleep, then that gave Gaston a chance to start. So Gaston started. And actually, each of them printed a message. So when Alphonse started, Alphonse got into, that's not right, sorry. It immediately got into run, generated a random number, slept for that amount of time. So Alphonse started first, then Gaston started. So Alphonse gave up the CPU. Okay, then Gaston starts and gives up the CPU. Now Alphonse wakes up and prints Alphonse's value. Print gives up the CPU. So when you print, you give up the CPU. So now Alphonse starts, wakes up, and prints Gaston's value. Print gives up the CPU. Okay, that is why we get value equal 20 and value equals 10, although you can see Gaston woke up first. So I got that slightly wrong. And the reason Gaston woke up first, presumably, is in the sleep, presumably Gaston slept less than Alphonse. Okay, so now, I guess what happens next, to be honest, is that Gaston wakes up and prints Gaston's value, gives up the CPU. Now, presumably Gaston comes back first because of what you see here. Gaston will come back first. And the next thing that happens is Gaston is here in add, so it printed this message right here. Now Gaston tries to get value from Alphonse right here. Whoops. Okay, so right here, Gaston calls Alphonse calls Alphonse's get value method. Okay, Alphonse has the lock, okay, but Alphonse has the lock. So Gaston sleeps. Okay, so now Alphonse wakes up because Gaston seated the CPU. And immediately calls Gaston's get value. But Gaston has the lock. So Alphonse sleeps. And like sleeping beauties, they sleep forever because neither is going to give up the lock it has. So at this point, you're in deadlock, and as you can see, it still hasn't made any progress. I've been describing the situation for 5 minutes, and they're still there. So they're clearly in deadlock. Okay, so I rewrote it using good lock. And before we do anything, I'm just going to run good lock to show you. It's not good luck. So let's go up here. Make it bigger. You can see it's already making progress. Alphonse value is 20. Gaston value is 20. Alphonse value is 10. Gaston comes back and gets the sum. Alphonse says, I want it to add Gaston's value to my value, but I can't obtain the locks for both my box and Gaston's box, and it backs out. It resets the value to 28 without completing the operation. Gaston sets its value to 39. Alphonse is able to add them to get 67, changes its value to 17, and you can see that again, Gaston is sleeping for a while, so Gaston's value is 39. Alphonse sums it, it's 56. And now Alphonse resets its value to 7. Gaston wakes up, prints out its value and Alphonse's value, adds them together to get 46. And you can see for a while, they run without a problem, but eventually there is a conflict again, and Gaston's unable to obtain the locks and backs out. So let's see what's going on and how they're avoiding this deadlock situation. Okay, so you can see they're coming. First of all, I'm getting this stuff from the locks package. So I'm importing lock and reentrant lock. And in my box class, I'm now creating a reentrant lock. And I've gotten rid of all my synchronized methods. So there's no synchronized methods. First, we'll look at add. So add, first thing it tries to do is obtain the locks. And it's going to have to obtain both locks for itself and for the person it's adding, whose box it's adding. So if it gets the locks, then it's able to add the values together, print them out, and as you can see, it then unlocks the 2 locks. So it gets its own lock and the lock for the adder. If it cannot obtain both locks, that's where it prints out the message, I want it to perform the addition, but I couldn't get both locks, so I backed out and didn't do it. Okay, so obtain locks is right here. So this indicates, these two Booleans indicate whether you obtained the locks. So this is a try. So you try to obtain both locks, and notice you're unwilling to wait. So if you fail fast, if you can't obtain either lock, you immediately fail. So if you can't get either lock, then one of these two will evaluate to false. So if you got both of them, if it's true and true, this if statement won't execute. But if one of them returns false, then this if statement returns true. It means that you did not get one or both locks. And so you check to see if you got either lock. And if you got one of the two locks, you do the unlock on it. So you immediately unlock to get out of the way. And then you return whether you succeeded or not. If you got both locks, those two variables are true. If you didn't get both locks, one of them is false, one or both is false, it returns false. Okay, so this isn't going to deadlock because either you're going to obtain locks is either going to immediately get both locks or it's not. But one way or the other, it's going to, if it gets the locks, it will execute this code. If it doesn't get the locks, it will execute this code, but it won't deadlock. Okay, and then if we look at set value, because remember what it does is it first adds the box and then it calls set value. So the set value can also cause a race condition because you don't want to be setting it while the other person is looking at it. So you also need to be careful with set value. So again, what you need to do is obtain the lock on yourself. And if you get it, you assign the new value and unlock yourself. If you do not get the lock, then you indicate that you failed to set the value because you could not get the lock. So again, you're willing to fail. The way we avoid deadlock is we back out of an operation if we can't get the lock for it. Okay. Now you didn't see that down here, so let's see if we can actually get, okay, here it was. Alphonse failed to set value because I could not get the lock. So in fact, very early on, Gaston was unable to get the lock and set value. So this shows you how you can synchronize actions between two or more threads. Now, this was a complicated piece of code here. The other one was simple. So you don't start using these mutex locks unless you have to. Synchronized methods and synchronized statements still probably fit the old 80-20 rule, which is probably 80% of the time you can use synchronized methods with 20% of the effort. And then the remaining 20% of the time, you'll need to use the mutex locks, and that will require 80% of the effort because they require a lot more code and probably more debugging because you may not get the race conditions just right the first time you do it. For example, if you forget that set value could cause a problem, you might find that if you don't put a lock on set value that you're getting some funny looking results. So it can take a little while to figure out what parts of your code have to actually be protected if you're not going to use synchronized methods anymore. Because you'll notice these things, I removed the synchronized methods and they're no longer, and they don't need any locks. Okay, so only use reentrant locks if you really need to, because they are more complicated. So questions about reentrant locks? Okay. So next, we move on to what are called thread pools. So a thread pool is a set of threads that are willing to perform a task. So a task is a computation you want repeated one or more times, and normally it's embedded in a thread. But let's take an example of how this could go badly for us. So that let's say we have a task, which is the task is to establish an HTTP connection with the client. Kind of like what you're doing with your chat rooms, okay? And let's say that it's a single server, and all of a sudden you get deluged with, say, 1 million. So let's say you generate a thread. Okay? Problem. If too many clients tried to connect at once. So for example, a denial of service attack. Let's say 1 million requests arrive pretty much at the same time asking for a connection. So you generate 1 million threads and your system pretty much grinds to a halt. Doesn't have enough memory, so it goes to virtual memory. Now everything starts swapping, and you're reading all the time from virtual memory. Nothing is running very quickly. The system appears to go down. Here's a second possible solution. Instead of generating a thread for each connection, make a connection be a task. That can be assigned to a thread. Okay, create a pool, a fixed pool of threads. Queue the tasks. And assign a task to a thread when the thread frees up. Now you can't overwhelm the CPU because there's a fixed pool of threads. So as the huge number of clients come in, they're quickly assigned to a queue, but only a fixed number of threads are running. So a bunch of people will have to wait for the connection, but at least some people are constantly getting a connection via this thread pool. So when the number of clients explodes, you don't go down. Instead, you just become very sluggish. But some people are always being processed on these threads. And in fact, you can process them much faster because the thread pool is fixed and you're not running out of memory. So that was the idea behind this executor or thread pool approach, was that you would not create a thread for each task. that you need to perform. But instead, you would separate the task from the thread. And you would have a thread pool with a fixed set of worker threads, and tasks are assigned to these worker threads as the worker threads become free. Okay, and that's done automatically for you by the Java runtime system. You don't have to do this matching. So one way this really works well is in terms of utilizing multi-threaded cores, or multi-cores, because now the Java runtime system figures out how to assign these threads to the different cores. You don't have to worry about scheduling. It can efficiently do it for you. So as it says, when a task is submitted to the thread pool, it is placed on a queue and ultimately executed by one of the threads, presumably a first in, first out queue. So executors are the classes that manage these thread pools. And just like cars have the basic model, the intermediate model, and the luxury model, executors come with increasingly full-featured services. So the most basic executor is a very simple one. They're all interfaces, and it just supports launching new tasks. So essentially, you create a task and give it to the thread pool, and the executor will ensure that eventually it gets executed. And as we'll see, you create a runnable for that. So instead of creating a thread, you create something with that runnable interface that we talked about, and then you submit it to the thread pool. Okay, then the executor service adds features to help manage the life cycle. So with the executor, you couldn't kill tasks. But with the executor service, you can kill tasks. You can have tasks return values, which you can't with an executor. So with an executor service, tasks can return values that you can use. And you can shut down the thread pools if you want, whereas with the executor, you can't. You just basically have to let those thread pools go until the tasks are exhausted. And then finally, your most full-featured executor service is your scheduled executor service, which allows you to schedule tasks at specific times and or periodic execution of tasks. So tasks that should be repeatedly executed, like, for example, a clock that moves its hand every second or every minute. Okay, so there's an executor class, and it provides a collection of factoring methods. So basically, factoring methods are static methods. So you call executor dot and then a method, and it will create thread pools for you, which will get managed by whichever one of the three interfaces you desire. Okay, so the most simple one is the executor interface. And as I said, your task implements the runnable interface. You put your code in a run method. You'll eventually call the thread pools execute method. And I'll have an example in a moment to show you how that happens. And then instead of calling new thread runnable.start, you simply call this execute method. Okay, so before I show you the thread pools in action, it's just a little more interesting if you can actually return a value. So these runnable tasks are like voids. They can't return any value. Sometimes you want a task to be able to return a value. So for that, you can create a callable task. And then you're allowed to return a value. And the way you get that value is that when the callable task is created, it creates what is called a future object and returns that future object. And then that future object allows you to access the result using the get method. It also allows you to cancel the execution of the task if for some reason you don't want to wait that long. So let me find, okay. So let's actually show you an example. So we're going to do the thread pool tester first. Hopefully you can see this. Okay. So what thread pool tester is going to do is essentially it's printing out messages with a value. So let's just run it, show you what's going on. So threads 1, 2, and 0 produce these random numbers. And let me put it to more. So the thread pool is has 3 threads, and we create 6 tasks. So initially, the first 3 tasks start executing, and they're generating random numbers between, I think, 4 and 77. So they print them out, and they generate 3 such random numbers. Okay, so 0, 2, and 1, they generate the random numbers. 2, 0, 1, generate the random numbers, and now they're done. So because they generate 3 random numbers, and then they're done. So now tasks 3, 4, and 5 pick up on those thread pools, and they produce their numbers, and that does it. So very simple. There's 6 tasks, 3 thread pools. I'm sorry, 3 threads in the thread pool. So so what we're doing is printing message, and we're given an ID, so that's our task number. And our run method for I equals 0 to 3, we simply print out our thread number, and we're using this concurrent thread random number generator to create an integer between 4 and 77. So we print it, then we sleep for 2 seconds, and we're willing to catch any interrupted exception. And then our thread pool tester, you can see we create a new fixed thread pool with 3 threads. And you see we create 6 print message tasks, and we execute them by calling the execute message. And I know after saying that you're supposed to use runnable, it extended thread. So that's fine too. Your task can also be threads rather than runnable. Okay, but it's heavier weight. Okay, and then at the end, after all 6 tasks had executed, I shut down the pool. Okay, and main, all it did was call new thread pool tester. So very simple. We created 6 tasks, and then we assigned them all to the thread pool, and you saw how the thread pool executed the first 3 tasks first, then the second set of 3 tasks. Now let's look at the callable tester. So a callable is a template or generic, and you indicate what kind of return value you are returning. So here we're returning an integer. And the only difference is that we when we generate the random number, we assign it to this random number variable, and the last random number we generate, we return. It's the only difference. Okay, now you'll notice the method is call. So the call method is returning this integer. So again, we get a fixed thread pool with 3 threads, and we create now an array list that's going to contain futures that are generated when we submit our task. So when we submit our task, it creates a future object that we can use to obtain the result. Okay, so the submit method is no longer execute. Remember, it used to be execute. Now it's submit. So we're submitting a callable. It generates a future which we add to our thread list. And our thread list is simply an array list of these futures. Okay, then after we have done that, for I equals 1 to 6, we get the future for that task, and we print out its value using get. Okay, so we will wait. That get method will cause us to wait until we get it. Okay, and again, we shut down the pool when we're done. Okay, so if we look at that, so it looks like 2, 1, it's going to go 2, 1, 0, and now the first 3 finished. And you'll notice that the last value for thread 0 was 7. The last value for thread 1 was 58. The last value for thread 2 was 45. You'll notice thread 2 finished first. Task 2 finished first, task 1 finished second, and task 0 finished last. But since the for loop went from 0 to 3, they're printed out in this order. Now, threads 5, 3, and 4 start executing. There's 5, 3, and 4. There's 5, 3. You'll notice that, in fact, thread 4, task 4 snuck in before it printed out the futures for 0, 1, and 2. So it went 4, 5, 3, 4, 5, 3. Then somehow 4 fell behind. But in the end, the futures were printed out again in the right order. Okay, so that gives you an idea of how this executor service works. Okay, and you saw an example of how the callable tasks work. They are executed using the submit method, whereas the so-called void methods that use runnable, they would be submitted using execute. Okay, the callables generate these future objects, which you can use to retrieve the value. It turns out you can also cancel execution of a future task. It has a method for doing that. And then you saw the shutdown methods for the pool. So it doesn't actually immediately shut down the pool. Instead, it simply says, I will accept no new tasks, but I will finish the execution of all my running and waiting tasks. So that's what I did. I called pool.shutdown as I came out of the loop, but that didn't actually shut down the thread pool immediately. It simply says, I will no longer accept any new tasks, but I will fulfill, it's like a shop that closes and says, okay, anyone who's in line, I will take you, but no new customers can get in line. That's what shutdown does. Shutdown now basically says, you're in line, go away. I'm killing you, okay? So not only can you not get in line anymore, but if you're in line, I'm not letting you in the store. So you might as well leave. It kills those tasks too. Plus, it tries to chase out anyone who's in the store. So it will try to kill any running task by calling interrupt. But you can be a stubborn thread and not die. So it can't, shutdown now can't force you out of the store. If you want, you can, quote, finish your shopping, check out, and only then do you get killed. So shutdown now accepts no new tasks, kills waiting tasks, and tries to kill running tasks by calling their interrupt method, but the task doesn't have to abide by the interrupt. It can ignore it. Okay, so shutdown now is a best effort to shut down the thread pool as quickly as possible. Okay, now another thing you can do with the executor service is what are called fork join pools. So this is designed for work that can be recursively divided into smaller tasks like sorting. So merge sort, quick sort are good tasks for that. And remember, modern CPUs have multiple cores. So you can, in fact, run parts of a sorting algorithm on different cores if you can get someone to manage that for you, which Java's happy to do. So basically, the pseudocode for these fork join pools is if my portion of the work is small enough, do the work directly. So that's like the base case. Otherwise, split my work into two pieces, invoke the two pieces, and wait for the results. So this is the fork. I'm sorry, the fork is invoke the two pieces. The join is wait for the results. Okay, so the way you do that is there's two subclasses. You can use a recursive task that returns a value or a recursive action that's like void. It does not return a value, but you could still, for example, operate on different parts of an array like quicksort does. And you use the invoke all method to submit a collection of tasks. And you don't have to, so this said divide it into two pieces. You can actually divide it into as many pieces as you want. And then invoke all takes a arbitrary length comma separated list of objects as parameters. And for each task, it returns is done when that task is done. Okay, so let's take a look at an example. So here is an example where you're sorting. So you have this array right here that you call an array of longs. And what you're extending recursive action. So this one does not return a value, but it operates on some portion of the array from low to high. And it checks first to see whether the portion of the array it is operating on is small enough that it can just sort it using something like selection sort on this machine or thread. But if it's too big, it calculates the middle and it calls invoke all by creating two new subtasks that operate on the lower and upper half of the array. And then it merges the array when it's done. So invoke all will only return when all tasks have been created. So effectively, it first forks. So this invoke all is both a fork and a join. It first forks these two tasks and then effectively does a join by waiting until each task is returned is done. And then only when all the tasks have returned is done does it move on to this merge, which is presumably a sequential method. Okay, so that is an example of, that's just sketching out a fork join sort. So then they give a more, a complete example where what they're doing is incrementing an array by 1. So they want to increment each element of an array by 1. And so they're doing the same thing. If the array portion chunk that's small enough, they simply increment each element of the portion of the array they were allocated by 1. Otherwise, again, they split low and high. I'm sorry, compute a midpoint, divide the array into a lower half and an upper half, and call invoke all on it. Now here, there's no merge because the two subtasks do the increment. So as soon as the join occurs, you are done. Okay, what I'm looking for is where you actually create a fork join pool. Okay, so initially the top level, you would do an invoke command in order to, so you create a instance of your task at the top level. You create one instance of it and you would call the pool's invoke method on that top level root object. So up here, you would create a single instance of an increment task, and then you would call pool.invoke on that single instance. And do they show, what they're not showing us is how you create a fork join pool. So let's quickly look up fork join pool. So presumably, what you would do is create a fork join pool with no arguments, because that will create the maximum amount of parallelism that Java can get for you. So basically, the idea is leave it up to Java to maximize the parallelism, because it can figure out how many cores the CPU has and optimize the number of threads it creates, thread pool it creates. So basically, you're still getting a thread pool here. And task, what you're doing is you were assigning, you were creating, in this case, two tasks at a time, two tasks at a time, two tasks at a time, and assigning them to this fork join pool, which creates as many threads as it thinks is optimal. And then it keeps assigning the tasks that you created to these threads until each of them has been processed. Okay, so that was our executor service. Now we go to our most full-featured one, which is our scheduled executor service, which allows you to schedule repeating tasks. So there's a difference between a fixed rate task and a fixed delay task. Okay, and so, oops, that's not what I want. So we have fixed rate, fixed delay. So a fixed rate guarantees that you will start up, say, let's say every 250 milliseconds. So at 0, your task will actually execute or be scheduled for execution every 250 milliseconds. It doesn't mean you'll execute immediately at 250 milliseconds, but you'll become eligible for scheduling them. So this is perfect for clocks because you want to essentially move the clock every so many seconds, the clock's handle. Fixed delay says, okay, you start at 0. Let's say you run for 10 milliseconds. Then you won't be scheduled until 260. So that's 250 milliseconds. That's a fixed delay. Let's say you start executing at 262 and you finish at 272. Then again, it will add 250 to that. And your next scheduled, you won't wake up again until 522. Let's say you're scheduled at 538. You finish at 550. Then again, you are not scheduled until 800. So you're drifting. This is called drift. Notice that the fourth instantiation here will start up at 750. Even if this finished at 10, the next one starts or can be scheduled at 250. Even if it finishes at like 270, the next one will start or be scheduled at 500. But here you have drift. So by the fourth time, you have a drift of 50 milliseconds. You're off. So fixed delay means you can drift. It's not good for things like clocks, which need to execute at a specific time. But it's fine for a lot of other tasks where basically you don't want to start up again until a fixed time increment after the current one. So sensors, again, would probably go on fixed rate. You want a sensor to take its measurements at a fixed rate. But there's other things where fixed delay works fine. Okay, so you can choose whether you're going to have a fixed rate or a fixed delay. And then you can, so this is a repeating event, and then you can cancel a repeating task by calling cancel on its returned future object. And in fact, as we'll see, you can schedule a something that will kill off a task also in the future. So for example, if you're running a animation for an hour and then you want to kill the animation in an hour, you can actually schedule a task an hour from now that's going to kill it, which is essentially what this is saying. You can schedule a one-shot task at a future time. So if you want to kill a repeated animation after 1 hour, you could schedule something in 1 hour to do it. So here is our final example of the day. It is of a beeper. So we are now creating a scheduled executor service. And we are creating, again, executors and calling the new scheduled thread pool with one thread. So there's only one thread in this pool. And let me just check some, well, I'll check it in a moment. Okay, so we want to beep for an hour. And we want to beep, I believe, every 10 seconds. So our run method is very simple. We print beep. That's our task. Very simple, we print beep. And we want to repeat this task every 10 seconds. So what we do is we schedule at a fixed rate. So every 10 seconds, our beeper task, which was created here, every 10 seconds, so 10 seconds, we could specify another time unit. And one of these two is a delay, so it won't start until 10 seconds from now, and then every 10 seconds it will run. And you can see it's returning a scheduled future, which allows us to cancel it whenever we want, which we do by creating a one-time task 1 hour from now. So in 1 hour, that's the delay right here. We are creating a task that you can see calls beeper handle got canceled. So in an hour, we in fact do call that cancel method on the future returned by the scheduling right here, and we kill it an hour from now. And that's it. It's very simple. So a very simple thing. You'll notice there is no effective return type here for it, so they use a question mark. If it could return a value, then you would put like integer or string or whatever if it could return a value, but it's not. Okay, so essentially if you want it to be void, you put a question mark here. And you might say, well, why not put void? Void is a primitive type. Okay, and templates can't take primitive types. Okay. So I think this is a bit of a hack. You also can't put object here because it's not returning an object. It's returning nothing. So I actually think this question mark is a bit of a hack on the part of Java's developers because void is a primitive type. It can't be put there. Okay, so basically your scheduled executor service, it just gives you the ability to create these repeating tasks, and it also gives you the ability to kill something in the future. What I wanted to check before I let you go, there's one thing I wanted to check. That is here. It's called new scheduled thread pool. Okay. What I want to do is check to, whoops. I want to check to see what the thread pool tester was. Okay, so here it was new fixed thread pool. And here it was new scheduled thread pools. So different so there's a single class, but with different methods, and depending on which method you call, you get the appropriate service that you want, okay? So there's actually, quote, not separate classes where you call the constructor. Instead, you have this one class you call a factory method to get the type of service that you're looking for. Okay, so with that, we have finished our discussion of concurrency. You won't be using these high-level concurrency methods in your homework assignment, but I might have questions in multiple choice form or multiple answer form on the final with them. So that's how I would test you on them on the final. I would not expect you to be able to write a piece of code with them on the final. I might expect you to be able to read a simple piece of code, but I think the most likely thing I would do with it is to give you some multiple choice questions. Okay, actually there is one final thing that I wanted. I know this is going to take a moment. I apologize, but there is something I wanted to quickly do at the end. There is 5 advantages, and I'll actually do that this way because it'll be faster. Okay, so there's 5 advantages addressed, or I will say thread disadvantages addressed by the thread pools. Okay, so one was they can't manage multi-core machines efficiently. Okay, 2, they cannot be killed. 3, they cannot return a value. 4, hard to handle massive concurrency. And 5, hard to schedule future or repetitive tasks. So these were the 5 disadvantages that the executor service was designed to address. Okay, so depending on which of the 3 executor services that you employ, you can accomplish all of these things. So for example, this was the fork join pools. Okay, this is the scheduled executor. This one is the most basic. And the next 2 was the executor service. So as you move up, you get different tasks that can be accomplished. So these 5 disadvantages were addressed by the thread pools. Okay, so as I said, this finishes up our discussion of concurrency. Starting Thursday, we start talking about our last topic of the semester, which is functional languages. So I will see you all on Thursday. And if you have